Hello student, welcome to MSc part 2. So in this semester I am going to teach you radicals in organic synthesis, which is unit number 2. Here is the syllabus. Unit 2, radicals in organic synthesis, paper 2. So this syllabus we are going to study in this semester. So radical, what is the radical? Radicals are the atoms, molecules or ions with unpaired electron, or a free radical may be defined as a species that contain one or more unpaired electron. So due to the presence of unpaired electron, free radicals are paramagnetic in nature. The unpaired electron is represented by dot. Life of a radical depends on its stability and condition of its generation. These species are generally short-lived species and extremely short-lived in a solution, but can have a longer lifetime in a crystal lattice. So the example of some radicals are hydrogen radical, chlorine radical, hydroxy radical, oxygen radical, methyl radical, then again ethyl radical, propyl radical, like this. So now we are going to see the difference between carbocation and carbanion. So this radical is like an intermediate, like your carbocation, carbanion, carbene, nitrogen, and it is highly reactive and highly unstable species. So how this differ from carbocation and carbanion, that we are going to see. So this is the image of your radical. Radical is a trivalent species having this dot dot indicate unpaired electron. When this, so what you can see that the radical having 7 valence electron, when this radical undergoes reduction, when it accepts the electron, it converts to carbanion, and carbanion having 8 valence electron, and the negative, there is a negative charge on carbanion. How it 8 electron? So I will tell you, 2 electron from this bond, okay, 1 electron shared by this carbon, 1 electron shared by this R group, same 2 here, 2 to 4 and plus 2 6, and 2 electron from this negative charge total. So total it having 8 valence electron. Now when this radical, carbon radical undergoes oxidation, when it loses electron, it converts to carbocation, and carbocation having 6 valence electron. Now next, in the next slide, this was the first radical, and the name of this radical is triphenylmethyl radical. So this radical was observed by Gomberg in 19th century. Although it took 13 more years to know what he had made. It can be generated by treatment of this triphenylmethyl chloride with silver radical. You will get this triphenylmethyl radical and AgCl. These are the other example of radical, hindered radical, that is tempo, phenalenyl and DPPH. The next point is generation of this free radical. How these free radicals are generated? A free radical is formed during a homolytic or homolysis of bond cleavage such that each generated fragment has 1 electron with it. So homolysis or homolytic cleavage occurs when certain wavelength of light or a photon fall on a compounds. There are two different types of vibration takes place. When a light fall on compound, there are two types of vibration takes place, that is vertical and horizontal vibration. So due to this vibration, there is a breaking of sigma bond homolytically. So here is the example how this bond break homolytically, and this single headed arrow is used to show the movement of single electron. So both the arrow are pointing opposite. It shows the movement of 2 electron, that is one electron moves to this A and another electron moves to another A. So by homolytic cleavage you will get this A dot is dot represent radical, you will get 2A radical. So in the next slide, how this radical are generated. So there are various ways by which radicals can be generated. So in that we are going to see these three, that is thermal cleavage, photochemical cleavage and redox reaction. So the first one, thermal cleavage. Free radical may be generated by thermal cleavage. In gaseous phase, some molecule break down at a high temperature. When the molecule contains bond with 20 to 40 kilocalorie mole of energy per mole of energy, cleavage can be caused in the liquid phase. For example, the thermal cleavage of azo compound yields free radicals. So this is your thermal cleavage. An example of thermal cleavage, this azo compound shows homolytic cleavage. In presence of heat, it converts to twice R radical and N2 molecule. Then second one is photochemical cleavage. So the name itself suggests that the homolytic cleavage or homolysis of sigma bond takes place in presence of light or a photon. So the energy of light, that is 600 to 300 nanometer, is 48 to 96 kilocalorie per mole, which is of order of magnitude of covalent bond energies. Certain molecule undergoes homolytic fission in the presence of light of that particular wavelength. For example, photochemical cleavage of chlorine molecule result into the formation of chlorine free radical. So this chlorine molecule in presence of H mu homolytically, the sigma bond between this Cl break homolytically, and you will get this twice Cl radical. Then third method is redox reaction. So radical can also be generated by redox reaction. So this here the example is Fe2 plus. When react with a hydrogen peroxide, oxidation reduction takes place. Fe2 plus convert to Fe3 plus, and this hydrogen peroxide breaks homolytically, and you will get 2 OH dot radical and 1 electron taken by this O dot and convert to OH minus. Now the formation of free radical is initiated by helper in presence of any of these homolytic cleavage takes place. Now what is helper? Helper is the long form of heat, electricity, light, peroxide and radical. So you can say that the bond breaking, the homolysis or heterolysis of the bond takes place in presence of this factor, that is heat, electricity, light, peroxide and radical. Next point is what are the characteristics of free radical. So the next point is characteristics of free radical. So in that, the first characteristic is free radicals are electron deficient species. So you know that the free radicals are electron deficient species. To understand this point, I am going to tell you one example, that is carbon radical. So carbon radical, carbon having 7 valence electron, it means that it requires one more electron to complete its octet. So that's why this carbon radical is a electron deficient. Then the second point is they are usually uncharged. So radical don't have any charge, like carbocation, carbocation having positive charge and your carbanion having negative charge, but radical don't have any charge. Then the third point is they contain odd number of electron. You know that the radical having odd number of electron, like 1, 3, 5, then 5, then 7, 9, 11, like that. Then the fourth point is alkyl radical has a 7 valence electron around the carbon bearing radical character. Then the fourth point is in methyl radical or alkyl radical, the radical center is trivalent and trigonally hybridized. So the radicals are trivalent. Then sixth point is the carbon is sp2 hybridized. The carbon is sp2 hybridized. Then 7th point is it has a planar structure. The 7th point is it has a planar structure. You know that the sp2 hybridized carbon are planar in nature, so that's why it has a planar structure. The geometry of sp2 hybridized carbon is planar. Next point is this is your methyl radical having this unfilled or it having half filled orbital, and the one electron, the unpaired electron present in one of the orbital, and that the name of that orbital is 2pz orbital, and that 2pz orbital sometimes it is called as SOMO means singly occupied molecular orbital, and this carbon is sp2 hybridized carbon. So the next point is 8 point. The unpaired electron occupies a 2pz atomic orbital of carbon. This singly occupied orbital is often referred as a singly occupied molecular orbital or SOMO. As stated by Pauli that the two electron occupying same orbital must have opposite spin and thus magnetic moment of such species become zero. However, free radical have a net magnetic moment is more than 1. So due to the presence of one or more unpaired electron, thus due to the presence of one or more unpaired electron, radical become paramagnetic, and thus it can be detected by ESR, electron spin resonance. By using this instrument, you can determine whether whether it is diamagnetic or paramagnetic. The next point is these radicals are highly reactive due to the presence of unpaired electron, which gets paired easily with another electron to fill their outer shell. So you know that the radical are highly reactive and highly unstable, so they react with another molecule to pair up to fill up their outer shell. Then next point is free radical combine to form a neutral molecule. When free radical react with another free radical, they combine to form a neutral molecule, stable molecule. Then next point is free radical can produce another free radical when react with neutral molecule. When free radical react with any other neutral molecule, it will convert neutral molecule. Next point is stability of a free radical. So since bond dissociation energy give us an idea of ease with each radical can form, they can also give us an idea of stability of those radicals once they have formed. The lower the bond dissociation energy, higher will be the stability. Alkyl radicals are stabilized by adjacent lone pair bearing heteroatom and by the pi bonds. The various factors responsible for the stability of free radicals are inductive effect, hyperconjugation effect, resonance effect, then hybridization, electronegativity, and polarizability. So we are going to see this one by one. So first one is your inductive effect. Greater the number of alkyl groups attached to the free radical carbon center, more will be the stability of radical. This is due to the electron donating inductive effect of alkyl groups, which decreases the electron deficiency of radical. The bond dissociation energy of CH bond for the formation of free radical of methane, ethane, and other alkanes clearly shows that radical center are stabilized by replacement of 1, 2, or 3 of the hydrogen of methyl radical by alkyl group. For example, the bond dissociation energy of ethane is 98 kilocalorie per mole, which is less than methane, that is 105 kilocalorie per mole. Thus the order of stability for the alkyl radical is tertiary is more stable than secondary is more stable than primary, and this primary alkyl radical is more stable than methyl radical. Now this alkyl group or CH3 group are electron donating group. It minimizes the electron deficiency of this carbon by plus I effect. So this tertiary butyl radical having 3 electron donating group, so it having more stability as compared to secondary radical, because in secondary radical or isopropyl radical it having only 2 methyl group, so it stabilizes less effectively as compared to tertiary butyl. Then this secondary butyl radical is more stable as compared to the secondary butyl radical is more stable as compared to this primary radical, because the primary radical having only 1 electron donating group, while in secondary it having 2 electron donating group. And the less stable is your methyl radical don't have any electron donating group, it having only this hydrogen, and hydrogen don't have any electron donating ability. So if electron donating group increases, it increases the stability of a radical, or you can say that it minimizes the electron density. It decreases the electron deficiency of that carbon by donating electron. So what are the electron donating groups? Alkyl groups are electron donating group like ethyl, methyl, propyl, butyl. These are the electron donating group. Then methoxy group is also electron donating group. Then amino group is also electron donating group. And then next, one more important point is free radical are destabilized by removing electron density. The group which is responsible for removing electron density from the radical, that group destabilize that radical. So what are the this destabilizing, what are this removing, what are we are going to see what are this destabilizing group, or which destabilize that radical. So that group is called as electron withdrawing group. Electron withdrawing groups such as NO2 group, then sulfonic acid group, then carboxylic acid group, keto group, then aldehydes, then aldehyde ketones. These are the electron withdrawing group. It withdraws electron from this carbon radical, because this carbon radical is already electron deficient. Again this electron withdrawing group removing electron towards itself. That's why it increases increases the electron deficiency. That and in another word, you can say that it destabilizes by removing electron density. So electron withdrawing group decreases the stability of a alkyl radical. Next point is your hyperconjugation effect. Hyperconjugation effect also give stability to free radical. As in case of carbocation, the stability order of alkyl free radical is tertiary, secondary, primary and methyl radical. This stability order can be explained by hyperconjugation effect. The odd electron in the alkyl group is delocalized into beta hydrogen through hyperconjugation. So you are having this your alpha carbon, this your beta carbon having this hydrogen, this beta hydrogen delocalized by hyperconjugation. The bond between this CH bond breaks homolytically. You will get H radical and C radical combined with this CH2, you will get this carbon double bond. This is your methyl radical. Same here, the image showing the hyperconjugation effect. So this bond will break like this, alpha bond will break by hyperconjugation. You are having C dot and H dot. Again that H dot is again the second hydrogen is showing hyperconjugation effect. It convert to H dot. Then these are the this image shows the stability order of your tertiary, secondary, primary and methyl radical. So in tertiary butyl radical, it having 3 alkyl group. It means that it having 9 alpha, 9 beta hydrogen. It means that it having 9 hyperconjugative structure. You can write the 9 hyperconjugative structure for this tertiary butyl radical. So this will be more stable. Then the second one, secondary butyl radical having only 2 methyl group. It means that it having only 6. You can write only 6 hyperconjugative structure, and for primary radical you can write only 3 hyperconjugative structure. So the stability order will be this to this. So tertiary butyl radical is more stable than this propyl radical. Propyl radical is more stable than this ethyl radical, and this methyl radical is less stable because methyl radical don't have any resonating structure. So as number of hyperconjugative structure increases, the stability of that radical increases. Next point is resonance effect. In the free radicals where the carbon center is in conjugation to the double bond. Here your free radical is in conjugation with the double bond. The resonance effect leads to stabilization of this molecule. The stabilizing effect of vinyl in allyl radical and phenyl group in benzyl radical are significant and can be satisfactorily explained by resonance. allyl and benzyl radicals are more stable than alkyl radicals. So here in resonance effect, if this ring is substituted with electron withdrawing and electron donating group, then that group affects the stability of that radical. If that substituent is electron donating group, that increases the stability of that benzyl radical, substituted benzyl radical. And if that group is electron withdrawing group, that destabilizes that that decreases the stability of that radical, or that destabilize that radical. Here the resonating structure of this allyl radical, the movement of this single electron, and this is the resonating structure of that allyl radical. Next point is radical stability decreases with increasing s character of the orbital. The stability of free radical decreases as the orbital is held more closer to the nucleus. So these are the three molecules. So this is your ethane. For our simplicity, I am calling it as a alkane, alkene, and alkyne. So alkane having sp3 hybridization, while alkene having sp2 hybridization, and while alkyne having sp hybridization. From this left to right, from sp3, sp2 and sp, the percentage of s character increases. As the percentage of s character increases, there is a low difference between your half filled orbital and nucleus. So in case of this alkyl, or it is also called as alkyl, so there is a more s character of the orbital, and orbital is closer to the nucleus. Higher electron affinity of half fill orbital to the nucleus, that's why it's having lesser stability. And while this alkyl radical are more stable, or alkane radical are more stable, and the reason is that it having less percentage of s character of orbital, further they are away from the nucleus, and the third most important is lower electron affinity of half fill orbital, and ultimately having greater stability. While alkyne, in between of that, alkane are more stable than alkene radical are more stable than alkyne radical. Next, radical stability increases with increasing electronegativity of atom. Across the periodic table, decrease in stability from left to right. So you know that in periodic table, from left to right, there is increase in electronegativity. So to understand this concept, I am going to give you example, that is this methyl radical, then this amine radical, then this hydroxy radical, and fluorine radical. So from carbon, nitrogen, oxygen, and fluorine, the electronegativity increases. Carbon is less electronegative than this nitrogen more electronegative than oxygen, and this fluorine is more electronegative than this oxygen. So electronegativity is increases from carbon to nitrogen to oxygen to fluorine. So as the electronegativity increases, the stability of that radical decreases. So carbon is less electronegative, that's why it's a more stable, while this fluorine is more electronegative, that's why it's a less stable. And the reason is higher electronegativity. It means that the greater electron affinity of half fill orbital, meaning it will be more unstable. So now nitrogen and oxygen center radical are quite unstable because that having high electronegativity. Next point, radical stability decreases as polarizability is decreased. So down the periodic table, increase the stability since the partially filled orbital is on the larger atom, and deficiency can be spread over a large area. So this iodine is iodine having big size, and it having more polarizability. So half fill orbital is on the larger atom, so its deficiency, radical electron deficiency can be spread over a large area. So this same case is absent in this fluorine radical, because fluorine radical, the size is very small, and partially filled orbital having very small size, and and the deficiency cannot spread over a large area. That's why fluorine radical is less stable. In halide, iodine is more stable than bromine, than chlorine, than fluorine. So this is the decreasing order of stability. Fluorine is less stable radical, and your iodine is more stable. Another example is this HSC, SH, selenium, thiol, and this hydroxy. So here the size of this HS is more, so the deficiency can be spread over a large area. So that's why this HSC radical is more stable than this hydroxy radical, and this is the stability order. So this HSC is more stable and hydroxy radical is less stable, and the reason is what? Partially filled orbital is on the uh, uh, smaller atom, and deficiency can spread over a smaller area. So that's why it's a less stable, and this HSE is more stable because what? Partially filled orbital is on the larger atom, and deficiency can spread over a large area due to its large size, large size or a big size. Now next slide. What you have to tell me the stability order for this molecule. So these are the benzyl radical, and this is a substituted benzyl radical, para nitro benzyl radical, then you have para methyl benzyl radical, and para methoxy benzyl radical. Now here you have to use your inductive effect and resonance effect. So to solve this question, you have to use your inductive effect and resonance effect on stability of a radical. So here this OCS3 para methoxy benzyl radical is more stable because this OCH3 group is a electron donating group. It gives its electron to the ring, and it stabilizes this benzyl radical. So the stability order is fourth one is more stable, then again fourth one is more stable because it having electron donating group. Then second most stable is this one, that is paramethyl benzyl radical. So second most is this one, because this CH3 is a electron donating group. It gives its electron by a hyperconjugation as well as plus Ra effect. So it stabilizes its CH2 radical. And the third most stable is this benzyl radical. Benzyl radical is more stable because it don't have any electron, it don't have any substituent, but it's stabilized by resonance. And the least stable is this second number is least stable because it having this nitro group is electron withdrawing group, so it destabilizes that CH2 radical, or you can see that it removes the electron density from this CH2. It removes the electron density, so that's why it destabilizes that radical. Okay, so this is the stability order, and this type of question are asked in the competitive examination like your NET, SET and GATE exam. The question may be asked, arrange the following compound on increasing or maybe decreasing order of its stability. So that time you should know the basic concept of that. If your concept is clear, then you can easily solve that questions. Then this is the general stability order. So benzyl radical are more stable. Why benzyl radical are more stable? Because in benzyl radical, the radical is stabilized by resonance, and resonance is more effective than inductive effect as well as hyperconjugation effect. So that's why benzyl radical is more stable. Then second most stable is allylic radical, because allylic radical is also stabilized by resonance. So second most stable is allylic radical. Then third one is tertiary radical. So this tertiary radical is stabilized by both electron donating inductive effect as well as hyperconjugation effect. So the third most stable is tertiary radical, then secondary, then primary, then methyl and vinyl radical. Vinyl radical is least stable because that radical is present on sp2 hybridized carbon, and the distance between your half fill orbital and your nucleus is very close, that's why it's a less stable. So this is the standard stability order for a organic compound: benzyl, allylic radical, tertiary, secondary, primary, methyl and vinyl. Now this question you have to solve. You have to solve the question, and you have to write down the reason, and you have to write the stability order of this molecule, and take a snapshot of that and upload in your Google Classroom. Thank you. If you have any problem, then you can ask me. Once again, thank you.